All right, welcome everybody. We're going to go over homework 6, chapter 28. Specifically here, we're covering magnetism. Now, before we get started, I just want to mention that we're going to kind of hit a reset here. We're kind of done with electricity, although we're still going to use it in some of the problems that we're doing, but we're not going to introduce any new electricity. Instead, we're sort of hitting the reset. We're going back to the beginning and talking about force. Just as we started with electric force, we're going to start with magnetic force, and we're going to build up from here. So we get to kind of hit a reset after the first exam, which some people appreciate. We do still need to know our first exam stuff, but we're not building on top of it necessarily. On the flip side, what I do want to mention is that this is going to be the most difficult uh, section. The next month or so is going to be the most difficult part of physics for most of you. And that is just to say that if this is not making sense on your first pass through, that's fine. That's normal. You're okay. You're going to make it. Okay. Don't let this bog you down too much. It is very counterintuitive and it gets very screwy very quickly. Let's talk about why it gets screwy. We're going to start with actually the definition of the electrostatic force, or one of the equations that we had, which was F equals Q times E. This is an equation that we use quite a bit. And what this tells you is if you have a charge that has a charged particle with some charge, and it is placed inside of an electric field, then it's going to feel an electrostatic force, which we now need to differentiate, right? It's going to feel an electrostatic force due to that electric field, and that electrostatic force is going to point in the same direction as the electric field. This is actually a little bit simpler than the equation that we are going to use for the magnetic force. Here's why. In order to experience a magnetic force, a particle needs to not only have charge and be placed in a magnetic field, but it also needs to have velocity. And we know we need to multiply them all together, but to put that all together, it gives us an equation that looks like something like, we know we're going to have a magnetic force, and we use B for the magnetic force and for the magnetic field. And so we know we want to have Q times V times B. But here's the thing, velocity and magnetic field are both vectors. So in order to multiply them together, I only have two ways of multiplying vectors together. It's either a dot product or a cross product. I can't just straightforward multiply them like I would with scalars. So it's got to be either a dot product or a cross product. And it turns out that actually the magnetic force gets bigger the more perpendicular the velocity is to the magnetic field, which means that this is a cross product multiplication. And this is the screwiness of the magnetic force. And this is where the difficulty kind of comes in, because we have to actually evaluate a cross product. This means also, I should mention, that if your velocity points in the same direction as your magnetic field, even if you are a charged particle, if your velocity points in the same direction as your magnetic field, you will not experience a magnetic force. All right, let's talk about how we actually use it. Just as we did with electricity, remember in electricity I made a big deal about doing calculations with the magnitudes and doing a picture to find your direction. We're going to do the same thing here. First thing I want to talk about is the magnitude definition. So we just sort of edit this equation a little bit to get a magnitude equation. Here I'm not going to have vector symbols on top of any of these, and that's just indicating that this is a magnitude equation. So we just have Q times V times B times the sine of phi. What we've done here is we've reduced this cross product so that we don't have to actually set up the matrix and do the cross product operation. We've reduced this down to just the magnitude of the cross product, VB sine of phi, where phi is the angle between the velocity and the magnetic field. And just to test it out, you can test out those 2 points that I just made. One of them is, what if the angle is 0? What if they point in the same direction? Phi is equal to 0, sine of phi is 0, and so you have a force of 0. On the flip side, where is it at a maximum? Well, that's whenever sine is equal to 1, and sine is equal to 1 whenever phi is equal to 90 degrees, of course 270. But whenever it's equal to 90 degrees, that's when you have a sine of 1, and then you have a maximum magnetic force. All right, so here's how we calculate, and we're going to use this quite a bit, but the direction is sort of its own animal, and that's because we have to evaluate a cross product. So how do we evaluate a direction for a cross product? I'm actually going to use, before we get into using magnetic fields and stuff, I'm going to talk about the setup that that we use to determine our direction for say a set of axes. So if I have an XY axis system like this, I know the XY plane is in the plane of my page, or the screen, I guess I should say. And I want to decide the direction for Z. I know that the Z axis would have to be perpendicular to both X and Y, but that means that it could either point out of the page or into the page, or out of the screen or into the screen. And so I have to do something called the right-hand rule. And I'm going to teach you my right-hand rule. There's a million different right-hand rules. Whichever one works for you is fine. I'm just going to teach you mine. I think that this is the one that I, after all of these years, just default to whenever I need to do a right-hand rule. And it doesn't require any like finger pointing or anything, so that's why I choose this one. Um, but okay, so let's go ahead and I'm just going to show you how I would do this. So I do what's called a finger sweep. So I point my fingers in the direction of my first vector and sweep toward the second. In this case, my first vector is x. I need to do x cross y. So I point my fingers. Let's see, my screen is flipped. So let me make sure I get it right. I point my fingers in the direction of the first vector. Good, like that, which is the x vector. And then I need to sweep in the direction of the y. So the y points straight up. So I want to sweep my fingers upward. And I sort of, I need to stay in the screen here. This is kind of the most fun to watch other people do for this exact reason. Um, but here we go. So I'm pointing in the direction of X, I'm sweeping in the direction of Y, and notice that my thumb, which will tell me the direction for the third vector, is pointing out of the screen. So that's what tells me that the Z axis in this case, let me make sure I line that up with the origin. The Z axis is going to point out of the screen or out of the page. Another XYZ axis system that you may have seen is one where X is coming out of the page and Y is pointing to the right. In this case, I would point my fingers in the direction of X. Now I want to sweep them in the direction of Y. So I point out of the page for X, and then I sweep in the direction of Y, and notice my thumb points up, and that will be the Z direction. All right, you're gonna have to do some practice with the right-hand rule. So if you're not getting this immediately, that's okay. The only way to get this down is to do some practice, and we're gonna do a couple of right-hand rules as we go through. There are gonna be some problems on the homework that you can only get if you do the right-hand rule. So let's go ahead and jump into a problem. We'll start off with problem number 1. Unfortunately, with the homework problems, we jump immediately into situations where we have both a magnetic field and an electric field. So we're going to have to bring the electric field in right away as well. But let's just go ahead and take a look at this guy right here. First problem, we have a proton traveling through uniform magnetic and electric fields. Fine. Magnetic field is in the negative x direction and has a magnitude of 2.69 milliteslas, whatever yours happens to be. Okay, so I have a magnetic field in the negative x direction. Now, the sign convention that I'm going to use in this class is going to look like this. I'm going to have to the right is going to be positive x, up is going to be positive y, and then z is going to be out of the page. It's the first one that I defined. In my diagram, the way that the z is actually going to be showcased is with this convention right here. This represents a z that is out of the page in the positive z direction. It's like the tip of an arrow. And this symbol is going to represent a negative z. This is a z direction into the page, and that's like seeing the tail of an arrow or a dart moving away from you. So you can think of an arrow, the tip of the arrow right here, and the tail of the arrow right there. Okay, so let's go ahead and again draw our picture. And keeping in mind that our third dimension is just going to be sort of shown in cross-section like that into or out of the page. And as we mentioned, we have a magnetic field in the negative x direction. So we can go ahead and label our magnetic field as a vector on our diagram. And the velocity of my proton is in the positive y direction. So that would be my velocity. And they ask for the magnitude of the net force if the electric field is in all of these other various directions. So first thing that we need to do is we need to get the direction of the magnetic force, and then we can talk about the electric force. So this is going to be a cross product definition. Remember, it's Q V cross B. In order to get the direction, I have to do V cross with B. So my right-hand rule is I point in the direction of V, and I'm going to sweep toward B. So that actually is V is going to point up, and then I sweep toward B, which is in the negative x direction. And notice my thumb is going out of the page. Make sure I got that right. And so that would be something like this. We can go ahead and label that as our magnetic force vector. So my magnetic force is coming out of the page. It's going in the positive z direction. Sorry, that little arrow there is probably going to confuse people. That's just the vector symbol on top of the F there. And cool, that's my magnetic force. And I know that the magnitude is just going to be QVB sine of phi, but it'll actually just be, for this problem, QVB, it's sine of phi. What is the angle between V and B here? Well, it's actually a right angle. So this will be sine of 90, which is going to be 1. So you could actually leave that off. But it's just QVB. And then I think we have Q because it's the proton. We have a V given. We have a B given. So we can go ahead and calculate that magnetic force. And then we just keep in mind that that's coming out of the page just in the positive Z direction. And then we have a few different options for the direction of the electric field. And the direction of the electric field, remember, will automatically give us the direction of the electric force because it's just Q times E. Wherever the field points is the direction your force points. And we just need to be able to add them together in terms of vector notation. So for part A, our E field is going to point in the positive Z, so out of the page. So that means that our electrostatic force, which is just going to be Q times E, is going to point out of the page. So I'm not sure exactly how to label it. I guess I could draw a diagram and say that, you'd have an E vector out of the page. Maybe that'll work. Or an F sub E vector out of the page. So this is the magnitude that you can calculate. And then we have our magnitude for our magnetic force right here. And then the way that we're going to add them together for part A, since they point in the same direction, they are vectors, but they're vectors pointing in the same direction. So the overall magnitude would come from just adding them together. All right, let's look at part B. In part B, it's going to be in the negative Z direction. So for part B, it's going into the page. So it's still going to have this same magnitude from part A, except now it's going into the page. So in order to get the net magnitude of the force, we have to do whatever the magnitude of the magnetic force is that we found right here, which is out of the page, and subtract this magnitude into the page because they point in opposite directions. So you have to subtract them. And then in part C, it's going to point in the positive X direction. So when it's pointing in the positive X direction, that is, of course, going to be to the right. So there's our direction for our electrostatic force in part C. And in this case, our magnetic force is out of the page, our electrostatic force is to the right. This is a 90-degree relationship. So in this case, the way that I would add, these two different magnitudes together, since they're at a 90-degree angle, is I would square them, add them together, take the square root, right? In other words, do the Pythagorean theorem. Okay, so we'll go ahead and move on to the second problem. I think this is also going to be similar. Yeah, this is going to be our block problem. So in this problem, we are dealing with a little thing. I don't think it's ever actually explicitly called this, but it's essentially going to be a this is called the Hall effect. And essentially what happens with the Hall effect is if you have a metal that's passing through a magnetic field, because the magnetic field is going to cause any charge to move through that metal to one side, you essentially establish a voltage. Now, the actual way that we would do any sort of calculation here is, well, the first thing that we need to notice is that when we are moving in one of our directions, we get a voltage that is 0, and they'll tell you which direction that is. But if your voltage is 0 in a given direction, that means that that is the direction that the magnetic field points. And so since our magnetic field is pointing in that direction, we'd say that the edge length in that direction is whatever is given in the problem. So that is, again, wherever your voltage is 0, that tells you that that edge length is equal to the given edge length. Now we don't know the other edge lengths, so we have to use the voltages that are, I guess it's the X direction. We have to use the voltages that are given and to do a little bit of calculation, so we have to generate an equation. All right, so here is what we know is the forces, the charge is going to distribute over this block. So let's just actually treat it like it's a bar that's moving in this direction through a magnetic field that is, say, out of the page. So we have V, we can do a right-hand rule here. We can say V crossed with B is going to tell us that positive charges are going to move down. And so you'd have positive charge build up on the bottom of the bar, and you'd have negative charge build up at the top of the bar. And this charge is going to move and build up this potential difference between the two ends of the bar. And it's going to build up until the magnetic force that's pushing these charges outward is equal to the electric force that's pushing them inward. So in other words, we want to build and build and build until our magnetic force is equal to our electric force. And at this point, then, we know the magnitude of the magnetic force is going to be QVB sine of phi, where again, phi is 90, and thus we just have a sine of 1. And then this will be equal to QE for the electric field. And this reduces down to an equation that we'll use quite a bit, which is that VB is equal to E. And often what you'll see is something like this. V is equal to E over B. This is an equation that you will find handy throughout our work with magnetism. And this is a good one to put down on a formula sheet or a note card or something like that that you're using to study. Right, okay, so we ultimately, in this problem, are given voltages in two directions. We need to somehow relate this to voltage. And the way that we'll do this is we can relate the electric field to the voltage. And we know the electric field is going to relate to the voltage via the equation delta V is equal to the integral of E dotted with ds. This is an equation that we used in our electricity chapter. And so long as our E is constant and our length is just the width of the bar, this will actually simplify down to just delta V is equal to E times whichever D we're looking for. So the last thing to keep in mind is that the D is going to be perpendicular to the direction of motion. So plugging these two things together real quick. So we have, we're going to substitute out for the electric field. It'll be delta V over a D. Let me make sure that I get all this right. So we'll end up with a little V. I'm going to put a little bar on this voltage V. And putting these two equations, this one and this one together, we're going to generate the equation that looks like this. The velocity or the speed is equal to the delta V, the voltage that is established, over B times D. Now, again, I mentioned this, but I wanted to write this out so that I can say explicitly, remember that our velocity has to be perpendicular to the length that we're actually trying to solve for. So that means that if I want to find, say, the x length, then I need to use the y velocity and vice versa. And that's how you determine the direction if you're parallel to the y-axis versus the z-axis. We actually already know the d sub x, but for the y and z, they would be related this way. So your y velocity would be related to your d length because those two will be perpendicular. And on the flip side, your z velocity will be related to your y length. All right, take a look at our next problem. The next few problems are going to have to deal with rotation. Why would we deal with rotation at all? Just to take a step back here and explain why we're dealing with rotation. Because a particle is moving with a velocity that is, if you have a field, we know that the magnetic force is always going to be perpendicular to that velocity, always. And if you remember from physics 1, when your force is perpendicular to your velocity, what that's going to do is that's going to cause your particle to turn. And so you actually will get some circular motion. And we can describe the circular motion in a few different ways. The one thing that we can do is we can relate our centripetal force to our magnetic force. So setting our centripetal force equal to our magnetic force. If you do not remember the centripetal force from physics 1, that's fine. I'm going to derive an equation here that you can use all the time. So our centripetal force is mv squared over r. And our magnetic force we know is going to be qvb. And then sine of phi, and phi is 90, and sine of 90 is 1. Just say that every time. And yeah, okay. So then we can solve here for any number of things. But this relationship will always work. We'd probably cancel out one of our v's, and you could have, something like v over r is equal to qb over m. You could rearrange this. You could solve for R. That's a very common one. So this would be the same thing as saying R is equal to, whoops, it's supposed to be get a nicer R there. R is equal to, what will we have? MV over QB. All right, you could rearrange this equation, and we're going to rearrange it to do some problems as we go through. One thing that I want to mention is since we have rotation, we can also talk about the period. Period was a common topic with rotation. You may need to actually calculate that. Remember, period is 2 pi r over v. And in light of this first simplification here, I know v over r is qb over m. So I can plug that in on the right-hand side. That tells me that my period for rotational motion through magnetic field will be 2 pi m over qb. So that's going to be a handy equation as well. And, just sort of all of these relationships, all three of these are going to be nice. We actually, if you wanted to put it on a formula sheet or something, you could probably just omit this part. I was just showing you the derivation. But the equation that you put down is that the period is equal to 2 pi m over qb. Let's go ahead and take a look at a problem where we are actually putting this to use. Problem number 3. We have a particle, we have an electron with the kinetic energy given, and we're given a magnetic field, and it's going to go through a half circle. It's going to exit. It's going to go through another region, and there's also a potential difference over the gap. So the diagram, my diagrams aren't even showing up, but I think I remember what this looks like. It looks something like this. You have a particle, it's coming in with some kinetic energy. It's going to rotate through region 1, and then it's going to jump the gap here, and then it's going to rotate through region 2, and then it's going to come out the other end. So I think it doesn't actually show it, but you'd have rotations in here in these regions, and these are each going to be half turns. And we want to find ultimately the total time that it takes to go through all three regions. So, oh, and the last thing is we have a potential difference right here. So we got a lot going on. We have a lot going on. We have magnetic motion in here. We have some electricity going on right here, and then we have more magnetic motion down here. Ultimately, if I want the total time, my total time is going to be equal to the time through region 1 plus the time through that voltage gap plus the time through region 2. Okay, so region 1 and region 2, the speed is not changing. We know that the time will just be related to the period formula that I just found. And in fact, in both of those cases, those are actually just half of a period because we're only undergoing half of a rotation. So T1 is equal to the period divided by 2, the period for that region. And the period equation is 2 pi m on qb. So you'd end up with actually like pi m on QB, where the B here is going to be field 1. And you'll notice it doesn't actually matter how fast this proton is going. You just need to know the mass and charge of the proton, or sorry, it's an electron in this case. And cool, that's we actually know that right off the top. We know the mass and we know the charge. So that's going to be your equation for T1. T2 is going to be identical. You just have pi m on q b2. And cool, those are good. That's actually, so the magnetism is actually not too difficult. The only part that we actually then have to do a little bit more work for is to find the time through the voltage gap. So what is going to happen in our voltage gap is we know that what are we given an electric, let's see, we're given a potential difference through the voltage gap, and that's all. And what we know is going to happen there is since the electron is moving over a potential difference, it's going to accelerate. That's the only place where it's actually going to gain speed. So through that voltage gap, we have some acceleration. How do we relate it? I know I generally want to do something like F equals ma. And I know I want to relate this to the magnetic force, the electrostatic force, because we're doing a voltage, which is Q times E. And then the last thing is, how do I actually find the electric field here. I have a voltage that I need to relate to an electric field. Remember, from the first unit in this class, we had that the electric field is equal to negative curly V curly X or curly Y or curly Z. We can actually, since we have a constant voltage here, we can turn this into um, a simplified version where it's just that the electric field is going to be equal to delta V over delta X. Now there's also a negative sign, but in this case, we're ultimately just looking for a magnitude for our acceleration. And we know that it's going to be speeding up. So that means that, let me make sure that I'm getting all of that down correctly. Yeah, so we can actually just sort of treat this as an absolute value because it will be moving in a direction. It'll be stepping down in voltage, and it's an electron. So maybe that's another way of putting it, is that since the electron, well, yeah, let's actually do that. That's how we should do this. Hold on. Let me go one step further here to make sure that everyone is on the same page. So yeah, so we'll go ahead and leave our negative sign there. And we're going to plug this in for the electric field. And so what that's going to give us is that MA is equal to Q. Now the charge of the electron is negative E. So we can go ahead and plug that in, times delta V on delta X, with also a negative sign out in front. And there we have then our two negatives that are going to cancel. And we will get a relationship for the acceleration. In this case, our acceleration is E times delta V over m times delta x. And yeah, great. That's our acceleration. And then the last thing is, if I want to find the actual time that it takes to traverse this gap, I need to do motion. And in order to do the motion, let me go ahead and sort of hope that you're all caught up in that diagram. In order to do the motion here, I have an acceleration. I know I'm also starting off with some velocity, and that velocity is related to the kinetic energy. So I start off with the kinetic energy. That's 1/2 mv squared. We could say that this is initial. And this allows me to solve for my v initial in terms of the kinetic energy. So I have 2 times the kinetic energy initial over m. So I have an initial velocity. I have an acceleration that I found down here. The last thing is then to just go ahead and do the motion. And I ultimately need to solve for a time. Well, the equation that you can use with everything else given here is that delta x is equal to v initial t plus 1/2 a t squared. So you can get kind of a gnarly equation here. You're going to plug in your acceleration, you're going to plug in your initial velocity, and you're going to have your delta x again right there. And you'll end up with a quadratic. Of course, these are, you know, the numbers for all these, so you can find the number for the acceleration, for the initial velocity, and so on. And you'll have a quadratic in terms of t, in terms of time. And you just need to solve that quadratic to find this time right here. And then, you know, these two times, you have to do the quadratic. And then once you find that time, you plug that in right here. And then we already know our 2 times for the magnetic portion, so those were actually pretty straightforward. And you go ahead and solve from there. All right, next problem is again rotation. Here we have something called a cyclotron. So a cyclotron has rotation, but it also has tiny gaps with voltages. And so the diagram looks something like this. You have like this chunk and this chunk, and there is a little voltage gap between these two chunks. So what the particle is going to do is it might start off at the center, or with just like a little radius, but it's going to accelerate over these gaps. So it's going to make the circle get bigger as it moves. Oops, bumped that with my arm. So it's going to accelerate. No, come on, don't. Please work. Good. And then accelerate over the gap, and then the loop will get bigger, and then it will accelerate over the gap. And so the radius of the loop is going to get bigger each time. Now, of course, it's not going to get bigger when it's in the magnetic regions, like up here and down here. But because of the way that the voltage gap works, it's going to gain some velocity. All right, so for problem number 4, we have a cyclotron problem. And we are actually just asked to investigate the radius. So let's see, it passes a gap, there's an electric potential, and yeah, so it starts at rest at the center, and then the potential is gonna it's gonna be subjected to the potential. So how much does the kinetic energy increase? That's a question. How does our kinetic energy increase? Part A. Well, I know that the kinetic energy can be related to the voltage gap. We could say that the change in the kinetic energy is just equal to the charge times the potential difference of the voltage gap. And so whatever your voltage gap is, you multiply by the charge. That tells you how much energy you gain on each jump through the little loop there. And in this particular problem, we're actually allowed to use something called electron volts. So this is very frustrating because even just on the last problem, we were using that the charge of the electron is negative E, the elementary charge. But we also will use E as a unit of measure to mean an electron volt. And that actually, well, it won't really factor in a whole bunch here, but it's just annoying that it's called an electron volt because it should really be called like an elementary volt or something like that. But anyway, the point is that you can actually just plug in E for the charge right here, and you're allowed to just use that in your units. So if it's 200 volts for your delta V, and it's a proton with an elementary charge E, then your answer would be 240 or 200 electron volts. All right, that's not the difficult part of this problem. Probably everybody got that. Part B, they asked what the kinetic energy is as it completes 122 passes through the gap. Well, we know that we're going to gain this kinetic energy on each one pass. If I want to do 122 passes, then my delta K would just be 122 Q times whatever the delta V is for the voltage gap. And then in part C, we have to do something a little more complicated where we're going to find the percentage increase between 123 and 122. And in order to find that percentage increase, we just need to consider the once trying to remember exactly the shortest path through this. You could calculate, oh, right, it's the radius. We're calculating the radius. So remember that we have a radius equation for part C. Our radius equation is that the radius is equal to mv over qb. Okay, cool. Now, I don't know the velocity here on each pass through, but I do know the kinetic energy. I can find the kinetic energy for the two different numbers that they give you. Here we found 122. Maybe they also give you 123. So that would just be 123 q times delta v. And then I just have to get a little clever with how I actually factor that kinetic energy in right here. So to go back to our last problem, we know that kinetic energy is a half mv squared. And this allows us to rearrange and say that the velocity is equal to 2k on m underneath the square root. Then we would just find our kinetic energy just like we did in part B. So for the first one, it'd be 122 q delta v. For the second one, it'd be 123 q times delta v. And we'd plug each of those in for the kinetic energy. And then ultimately, we would plug this in for the v up top. So what would that give us? We're going to have something like this. I'm going to use an n. Whoops. Oh, didn't think I was in eraser mode. I'm going to use an n for this number so that I can give kind of a general equation for the radius sub n. And it would be that radius sub n for some number of turns through the gap or jumps over the gap will be equal to m on qb times the square root of 2nq delta v on m. So I just did the two substitutions that I mentioned. I plugged this in right over here. Whoops. And then I plugged this whole thing right here in for the velocity up top, or the speed up top. And I get this kind of long, kind of arduous equation. But this will just allow me to plug in some n value, be it 122 or 123 or 500 or whatever. I can just plug those in right there and then solve for the percent change, which is just kind of a frustrating thing to ask us to solve for. because you're not going to necessarily find anything illuminating from your answer. You'll just get a percentage out at the end. All right. The next problem is another cyclotron problem. We're going to move through a radius. We're given the magnitude of the field. And here they ask us for the, first of all, the frequency. All right, so how do I find a cyclotron frequency? Well, remember I had that the period was equal to 2 pi m on QB. And I know that frequency is 1 over period. So since frequency size should be separated a little bit here. Since frequency is 1 over period, that means that my frequency is just this inverted. So QB on 2 pi m. And let me make sure that it's that simple. Let me just plug that in. Let's see, we have that it's a proton, so that's our Q and our M. And then we also have the magnetic field. Cool. So that's sort of all you need to do for part A. And then for part B, we are asked to find the kinetic energy of the proton. And in order to find the kinetic energy, I simply reverse the equation that I had on the last page, where that was sort of an intermediate equation. Okay, so I had that, let's see, I can use the radius. I know that the radius is equal to mv over qb, and I know that my kinetic energy is equal to 1/2 mv squared. So I know I need to use these two equations together. Ultimately, the unknown, the thing that's going to link these two together, I know the mass, right? So I could find the mass for the kinetic energy, but I do not know the speed. So I can solve this first equation for the speed, which will give me v is equal to q, oops, q br over m. And then I can go ahead and plug that in for the v and the kinetic energy, and I should have everything there because I have the radius. So I go ahead and plug it in. So what is the sort of lesson of all these cyclotron problems is that your most important equations are going to be this period equation and this radius equation. And we're going to talk quite a bit about kinetic energy, and we know kinetic energy relates to Q times delta V. But these two are the most important equations when you have that circular motion. To find, the radius of the motion or the period or something like that. Cool. All right. So the last thing that we're going to talk about now is we're going to go ahead and discuss currents. So we've already talked about a current. It's charge and motion. Why is a current important for magnetism? Well, that's because magnetism requires a charge to be in motion. Remember, it's QV cross B. You have to have a charge with a velocity, and current passing through a wire is just charge with velocity. So we adapt our magnetic force equation that we've been using, Q times V cross B. We can adapt this for a current. Oops, not an absolute value. We can adapt this for a current by simply noting that Q times V could also be, since V is distance over time, you could move that time on the bottom to under the Q. And so when you do that, you'd have a current out in front. And then what you're left with inside, since we had distance over time and we took the time, sort of factor the time up front, you're left with just a distance. Distance in terms of a wire is just going to be a length. So you have a length crossed with B left over inside. And here we have a new equation for the magnetic force, this time on a wire carrying a current I through a length L and a magnetic field B. And now we have to do a right-hand rule again. How are we going to do the right-hand rule? Well, here's an example where we have a power lines carrying a current from south to north. And I'm going to do, let's see, we're going to be our magnetic field is going to be toward the north, but at an angle downward. Okay, so I'm going to draw like the ground here. Here's the ground. And we're going to have our power line strung between these two poles. And we're going to be carrying the current from the south, which we'll put on the left-hand side, up to the north. And here's going to be our power line right there. So our current is flowing from south to north. That's what that little arrow means. And that's going to give us our direction for our length vector. And then they tell us that the Magnetic field is going to be directed toward the north, but it's going to be inclined downward 73 degrees to the horizontal. So my magnetic field is going to look something like this. Here's my magnetic field. And the angle that it makes right here is 73 degrees or whatever yours happens to be. Again, I need to do a right-hand rule here to find my direction. And I know I need to do L crossed with B. How is that going to work with the current? Well, I just point my fingers in the direction of L, which is pointing in that direction, and then I sweep in the direction of B, which is down, and that means that my thumb, let me make sure that I'm doing this right, L cross B, so my thumb is pointing actually into the screen. So my magnetic force then, right here, is going to be into the page. And then it's just sort of up to you to determine what direction that would be using sort of your never eat soggy waffles. So if north is to the right and south is to the left, that means that I have the eastward direction coming out at me. That's sort of, that's a weird way of putting that. I shouldn't have drawn it like a vector necessarily because it's not a vector, but you'd have like east coming out, and then that would mean that west is sort of going into the page just according to the way that I've drawn it. And then to actually do the calculation, just like we did with this equation, the magnetic force on a particle, we're actually going to do a calculation of the magnetic field using ILB sine of phi. And in this case, we have our current, we have our magnetic field. They give us a length for the line to use, and then sine of phi is going to be whatever the angle is that's given. So we'll finally use an angle for this problem. And the next problem is one that I do need the diagram for, I think. No, you know what? I think that'll be fine. Okay. So this next problem, there's two ways to do it. And I'm going to take a second here, and I'm actually going to do both. First, I'm going to grab a sip of water. But we have sort of an, I guess, what I'll say is there's an easy but incorrect way to get the right answer, and then there's a more difficult but more correct way to get the answer. So, I'm going to start with the first one, I think. Let's see. So we have a wood cylinder, and they give us the mass and the length, number of turns, and it's going to be released on a plane that makes an angle, and the coil is parallel to the angle, and then there's a vertical magnetic field, and they ask what the current is through the coil that keeps the cylinder from rolling down the plane. And no, I'm not going to do the incorrect one. I'm just gonna go ahead and talk through the actual correct one. So whenever I have a coil of wire, let's go ahead and just cover this theory. The last two problems both have to do with this. Let's just go ahead and do it. I'm going to have a coil of wire that's sort of coiled like this, and I will subject it to a magnetic field. And what's going to happen is this coil of wire is going to want to turn to orient toward the magnetic field. So if I have a magnetic field that points like this, and there's a current that is passing through the wire, cool, establish the right direction. Essentially what's going to happen is this coil will orient itself until the magnetic field is perpendicular to the coil. So the coil will rotate some, just a little bit, until you have a coil that, let's see if I can get this right, that is sort of oriented like this, and your magnetic field is now just pointing straight through. So there's something like a magnetic force here. But in fact, since we are causing a rotational motion, that force is causing rotation, we have what is called torque from physics 1. All right. So the torque on the wire is due to due to the magnetic field. But what we do is we actually define another vector that points perpendicular to the coil of wire. And this vector is called mu, and it is the magnetic dipole moment. And mu is equal to NIA. Notice I haven't put a vector on here. If you were going to put your vectors on here, mu would actually be equal to Ni times the area vector. That would be like a proper definition. But all you need to know is that mu is just perpendicular to the loop, and also that mu always wants to rotate until it points parallel to B. So that's what we've done in this second diagram over here, is that mu has rotated a point in the direction of B. All right, so just to talk about this definition, this equation for mu, we have n, which is the number of turns for the loop, I is going to be the current through the loop, and then A is the cross-sectional area. So like in this case where I have a circular loop, it would be a pi r squared, and those all together determine your mu. And then the actual torque on the loop is actually just equal to mu cross B. And this allows us to just write the magnitude of the torque as N I A B. And then again, we'd need a sine of phi. All right, so in the problem that we have, in this problem that we're doing, problem number 7, oh, I have to clear out some of these whiteboards. Hit my maximum very quickly this week. Okay, now I can make a new one. I can only make 12s and I have to delete. All right, so yeah, so in this problem, I have this inclined plane like this that has an angle theta, and I have the block. I'm going to do this sort of from the side. So my coil is kind of sitting on here on that block, right? And it's like a log, and the log is allowed to rotate. But all the important stuff right now is just to get the direction of my vectors down. So I have my mu like this, that's going to point perpendicular to the inclined plane. And then I know that I have a magnetic field B that is also pointing perpendicular. And whatever this theta is down here, if I were to follow through on all of my angles, that's going to be the same as this angle right here. Remember, that's the one that's important for calculating the actual torque. We need to know the sine of phi right there. That's going to be the same theta as the theta of the incline, just from the geometry of the problem. All right, now there's going to be some torque here because we know that mu wants to align in the direction of B, but there's also a torque pulling it in the other direction, and that is going to be the torque due to the friction. So to put those two together, we need to keep in mind that I have a circular log, and there are forces on this log. So I know that there's going to be the component of the gravity down, mg sine of theta, and then I know that there's going to be the friction acting up the ramp. Now, you're probably not going to remember this from Physics 1, okay? But from Physics 1, we know that the location of the force with reference to the center of gravity of the object determines whether there's a torque or not. Remember that in general, the torque due to a force, if you don't remember this, the torque is equal to Rf sine phi. Maybe this sounds familiar. And since we have to have an r, the r is going to be the distance from the center of mass of the object to the actual force. Now, my gravity, my weight, is applied at the center of the object. So that means that the torque from this guy is equal to 0. So it's not going to come up in our torque equation. But my friction is actually going to be located at the point where the log meets the incline. And so that friction is going to have a torque. And in fact, it'll have a torque that's just r times f. So putting all of this together then, we can sum our torques. This is what we do in Physics 1. You sum your torques. You'll have that little r times F, the force of friction, in one direction. And then the torque from the magnet. What's going on here? Is this applied at the center of the object? No, actually, this isn't a force operation. This is just a torque that occurs because of the magnetic field, so that you will always feel that torque. And we know that it's going to act counter to the direction of the friction. So we'd have Rf minus mu b sine of phi, and we know that our phi here is going to be the same as that theta, as we've already said. And then if you remember from physics 1, we do sum of the torques, and then we sum up the torques, we set it equal to I alpha. But since we don't want this thing to rotate, we can set it equal to 0, and alpha of 0. All right. Now we need another equation. We need to somehow deal with the friction. So that's actually going to come from a consideration of our forces. And the force equation is much simpler. We just have our mg sine theta in one direction, and we have our force of friction in the other direction. And so putting those two together, when I sum the forces that are parallel to the incline, I have mg sine of theta in one direction minus the friction in the other is equal to 0. All right, there's a whole lot going on here, but what I essentially have is just two equalities. The first one from the torque equation is Rf is equal to mu b sine of theta. Mu we know is Nia. So we have Nia b sine of theta. And then our second equation will give us a second equality. Mg sine of theta is equal to the force of friction. Whew, that's a lot to set up. Ultimately here we need to remember what we are given and what we are not given in the problem. We're given m, we're given g, we're given n. We are not given the area, so we need to replace the area, but we are given b. So two things we need to do is we need to get rid of the friction. Well, that's actually just going to come from taking our second equation and substituting it into the first, and then our friction is good. So the left-hand side just becomes r times mg sine theta. The other thing we need to deal with is the area, the cross-sectional area, and because of the way that the coil is wrapped around our log, it's rectangular like this, and we know that this distance right here is L, the length of the log, and then these are the circular faces on the side. So what is the length of a circular face? That's just, in other words, the diameter. So it'll just be 2 times r. So to put that all together, then the area is just 2RL. So we can go ahead and replace our area on the right-hand side of this equation with 2RL. Then we have mg sine theta on the other side. And then we can solve for, in this case, we're solving for the current ultimately. And your radius will cancel out of both sides, which is good because we also do not have the radius, I don't believe. All right, a grisly problem. It's a grisly problem to jump into. But we have one more, also dealing with the loopable wire that also has a moment of inertia. And this one's just going to be a little bit more of a algebra problem. All right, so we have a wire with a given length. And we're going to take that wire and we're going to wrap it up into a bunch of coils. We don't know how many, but we know our total length is going to be constant. And we're going to pipe a current through it, and we're going to place it in a magnetic field. And they ask us to maximize the torque on the coil. And they ask, what is the angle between B and the coil's magnetic dipole moment? Well, remember that the coil has a dipole moment that is always perpendicular to the coil. And we know that dipole moment always wants to point in the direction of B. So we know that when B is pointing in the same direction as the coil, there's going to be no torque. Your torque is 0. And then as B takes an angle, your torque is going to increase and increase and increase. Where is it at a maximum? Well, remember, torque is just mu B sine of phi. So your torque is going to be at a maximum whenever sine of phi is at a maximum, which is when sine of phi is 1. Okay, and I'll leave you there. I'll let you find the answer from there. Then they ask us what the number of turns in the coil is to maximize the torque. All right, so how do I determine my number of turns? Well, in this case, the number of turns is going to go into mu. So maybe what I'm trying to do here is maximize mu. So let's take a look at mu. Mu is Nia. Now, as I increase the number of turns, I'm going to increase n, but I'm also going to affect A. Here's why. I have a given length for this wire. As I coil it up, I will cause a tighter and tighter coil to form, which means that my cross-sectional area is actually going to decrease. All right, so what that means is that the length of the wire is equal to the circumference, 2 pi r, times the number of turns, n. And uh, ultimately, I know I want to calculate the area. So that means that I want to solve for r. So r is equal to L on 2 pi n. And then the area, which is pi r squared, will just be equal to, let me make sure I simplify correctly here. It'll be L squared on 4 pi n squared. All right. So here's my cross-sectional area. I can plug that in for mu. And now I have that mu is equal to ni times L squared on 4 pi n squared. Cancel out an n from top and bottom. And you'll notice that we have a relationship between mu and 1 over n, or some constants, but n is on the bottom. So that means that in order to make mu as big as possible, which we want to make our torque as big as possible, we need to make our n as small as possible. So think about what the smallest possible number is for the number of turns. The takeaway here is that if you want to maximize your torque, then you want to maximize your surface area. Don't worry about the number of turns, it's all about surface area. Last thing is to find the magnitude of the maximum torque. In this case, we have this relationship for mu. Just to tighten this up a little bit, this would be I L squared on 4 pi n. And then we'd go ahead and plug this in over here. We know we're going to make sine of theta be equal to 1, so we're good on that. We know our current is given, we know L given, 4 pi is constant, and we've just found in part B. So, and then we also have the field. So you just go ahead and plug in all of your stuff and go ahead and find the value of that torque. All right, so again, I want to take a step back here and just say, like, this stuff is incredibly difficult. And there's not a lot of build here, I don't think. And these problems are just very gnarly. It's okay if you don't get it. It's totally fine. This does not determine your worth as a person. It's going to be fine. Okay. We're going to get through this. And countless students have gotten through it before. If you've already made it to this point in your physics education, you can get through this. This is not going to be the thing that's going to break you. It is going to be challenging, but you got this. All right. And on that note, I will be posting another video this week. I will resume my usual office hours on Tuesday and post next week's homework a little bit ahead of schedule. I really appreciate everyone being patient with me this week in light of everything that's going on with the exam and with personal stuff as well. So yeah, great. All right, everybody, have a good week and keep your head up. All right.